1992-93 year. If you would all please stand, we'd like to open this evening's program with the Pledge of Allegiance, followed by an invitation written especially for this evening by Michael Cesarano. He will be backed up on vocals by Don Bicidal, Jerry McCoy, and Jim Gerard. Thank you. We'd now like to have our invocation. Thank you, gentlemen. That was beautiful. I'd like to introduce to you the 1992-1993 NKMA Board of Directors. First, our president, Al Parrish, as you all know, or some of you may not know, has been in the hospital for a quintuple bypass surgery. And I talked to his secretary today, and he's doing just fine, and he should be in the hospital for about 5 more days, and then he'll be going home. If you haven't signed the Get Well banner for him, it's out when you first came in. If you haven't signed it, please do so after this evening's speaker. Myself, Laurel Lichtenberger, I'm the vice president this year. Our secretary, Betty Godfrey. Our treasurer, Kathy Ruggieri. Professional development, Kathleen Hare, and I think Kathleen's here this evening, and Tom Yensko. Our programs, Jane Hodges and Jay Diggs. Public relations, Larry Mock and Judy Kersey, and I think Larry's here. Membership, Vicki Hall and Laverne Woodard. Finance, Louise Boyd and again Kathleen Hare. Booster, Retha Olson and Doris Castro, and Ruth is here. Okay. Recognition and awards, Gary Johnson and Larry Mock. And future planning, John Biddulph. Now, if you have any comments or questions or would just like to talk about NKMA, we encourage you to contact any of these people, and they'll be glad to have a discussion with you. Al would like to express his appreciation for over 30 members participating in our first Adopt a Shore cleanup activity that took place on Saturday, September 19th. We gathered over 268 pounds of trash and had a wonderful barbecue to celebrate. If you'd like to join this community activity and join us for our next cleanup weekend, we ask that you call John Biddulph. We would also like to encourage you to join us in some upcoming events. Now, the program committee has worked extremely hard to plan some fun and interesting programs for you. October 30th, we're planning a casino night at the Veterans Memorial Park with complimentary drinks and hors d'oeuvres, and I understand that's going to be just a rip-roaring night. November 11th, we've got Dr. Ed Wyckoff will speak on total quality communication at a dinner meeting at the Howard Johnsons. December 4th is one of the highlights of our year, our Christmas party. It will be a dinner dance at the Hilton. Then we start off the new year with January 29th, and we're going to have Colonel Fred Gregory, astronaut and associate administrator for safety and mission quality at NASA headquarters. He will take us on a shuttle ride to tomorrow at Space Camp and update us on headquarters activities over a buffet dinner. Then we go into February, and Jay Honeycutt will moderate a panel of our KSC engineers that have been active in the schools through the Education Branch's Engineers Speakers Bureau. We'll also be entertained by program committee members at Brevard Community College. Now, later on in the year, March 18th, we'll hear from McDonnell Douglas engineer Rick Vargo. I think Rick's here this evening, who recently returned from the New Russia with an update of their space program. Lasita Country Club will be the spot. April 28th, we bring George Gay, who will share his movie Battle of Midway and experiences as the sole survivor of the Torpedo 8 Squadron during World War II, and that will be, of course, at the Valiant Air Command. Now, a highlight of that evening is we will have a tour of the facility with hors d'oeuvres. May 22nd will be our luau at the Holiday Inn, and we've had one in previous years, and that always proves to be a fun night. Then we'll wrap up this year with our June 18th. We'll be learning about endangered species at the Gator Jungle, which is right over here in Christmas, Florida, I believe, with a social hour and hors d'oeuvres, including alligator meat. And they'll be providing a boat ride if you'd like. Now, for this evening's program, I would like to call Jane Hodges up. She's, like I said, our program chair for this evening. She's a specialist with the Public Affairs, Education, and Awareness branch, and she will introduce to you this evening's speaker.
Good evening. It gives me great pleasure to introduce my longtime colleague and friend, Dr. Farouk El-Baz. Farouk has been an avid supporter of education programs for teachers and students throughout the United States with such organizations as the National Congress on Aviation and Space Education, and also through the World Aerospace Organization as a fellow board member, and I've had the opportunity to hear him speak from Africa to the Mideast. He's a world-class scientist. He's served as advisor to the President of Egypt. He's taught geology to the Apollo astronauts and helped select the lunar landing sites. Born in Egypt, he has long been a citizen of the U.S., where he was educated at the University of Missouri and MIT, and now is the founding director of the Center for Remote Sensing at Boston University. He is also one of the foremost experts on deserts, studying almost every major desert in the world. Most recently, he helped assess the Desert Storm war damage on the country of Kuwait, returning just a few days ago. Also, this month's U.S. World and News Report discussed an article on remote sensing techniques on Egyptology. Other accomplishments include the Apollo-Soyuz Test Project Principal Investigator for Earth Observations, establishing the Center for Earth and Planetary Studies at the National Air and Space Museum of the Smithsonian, serving on committees for the National Space Foundation and the U.S. Board of Geographic Names, to mention just a few. Among the hundreds of honors and awards that he's received are our NASA Apollo Achievement Award, and the Exceptional Scientific Achievement Medal. I present Dr. Farouk El-Baz.
Thank you very much, Jane. Good evening, everyone. I'm delighted and honored to be the first speaker in what promises to be a wonderful program for this year. And the title for my presentation is From Apollo to Desert Storm. And this title actually kind of takes me into a journey through my career of nearly a quarter century of fascination with satellite images or photographs from space. As my colleague and friend Jane mentioned, I am the director of the Center for Remote Sensing at Boston University. And perhaps many people in the room don't really know exactly what this remote sensing is. It is a term that I personally fought for a long time. It is a fancy word for space photography, but we actually did not generate that term. It was generated in the Office of Naval Research. So oceanographers are the ones that actually started it. When we began working with the Apollo program in the very beginnings of it, the oceanographers at the Office of Naval Research had been going over programs for ocean sensing. This is whenever a Navy ship goes out, they have the instruments to measure the temperature, the salinity, and things of the ocean and so on, and that is called ocean sensing. So when they learned about the fact that these bunch of scientists are working with NASA to do imaging of the Earth from space, they said, now we can do our ocean sensing remotely. So it will be remote sensing. NASA engineers heard the term and loved it because it implies magic. So no matter how we actually fought this term, I'm now stuck with it, and I'm stuck with it as a director of the Center for Remote Sensing. However, in the simplest form, remote sensing is really studying something without having to touch it, or investigating a phenomenon from afar, from a distance. So if I go to a medical doctor and he checks my chest with an X-ray machine, he is really using remote sensing technology, because there is a black box that emits the X-rays towards my chest. The X-rays go through the body, and the result is recorded on film. The doctor takes that film, he looks at it, and he explains what is happening to me. And that is really, in the simplest form, that is exactly remote sensing. You depend on an instrument to see through something, whether you can actually see it by the eye or not, and then you take a picture of that and you interpret what you see. So now if we have an instrument that can actually go on the surface of the ground and send rays towards the Earth, and these rays are reflected back, and the reflections are recorded, then I can get the layering or the subsurface layering of the Earth. That is utilizing remote sensing technology. If I take a camera or some other sensor and I put it in a balloon or a kite that looks from that kite or the balloon down towards the Earth and also gives me a picture of that area that it sees, that is remote sensing. And when I take that onto an aircraft or a spacecraft, it's the same thing. Now, as Jane said, I've also kind of emphasized the study of the desert in general, in satellite images. And the reason for that is more cultural than anything else. I am a geologist. I came from Egypt, a country that is 96% desert. And I found that throughout my education, I have really learned very little about desert. Even though I was educated with first-rate professors in Egypt, and I came here and I studied at the Missouri School of Mines and Metallurgy, part of the University of Missouri system in Rolla, Missouri, and then did my research at MIT in Cambridge, and actually I went to Heidelberg and spent a couple of years there at the Max Planck Institute at the University of Heidelberg, and I thought I rubbed shoulders with some of the finest geologists of our time. And then when it came to really understand what is there in the desert, I realized that we know very little. When I'm studying geology at Ain Shams University in Egypt, I learned everything there is to know about the Himalayas, the Alps, the Grand Canyon, the Paris Basin, the Scottish Diapirs, and the Himalayas, and very little about the desert outside of the classroom. And that bothered me as an Egyptian geologist. And they thought about it, and they found that there are really three very basic reasons for that. For the fact that we know about most other features of the Earth, but not as much about deserts. The first reason is that Earth sciences or geology began in England, France, and Germany. And Europe is the only continent on Earth that does not have a desert. So the fathers of geology or Earth sciences never really had examples of arid landforms to write about. And those who came after them did the same thing, and those who came after them did the same thing, until today. You find a book on geology or geomorphology without a single chapter on arid lands. So that's rather basic. The second reason is the fact that the desert is huge, vast, and the conditions in the desert are also harsh. Very few people would really venture into the desert. If you have a graduate student who wants to pick up a topic for a master's thesis, he's going to want to find some place where you can go to the field, and then after you go to the field, you go down to a bar and have a beer or something and so on, and you're in the desert. There are no bars, there are no hotels, there is no water. Why would you select a place like that to go and study it? The third reason is also more basic to our understanding of the geological profession. We geologists tend to fancy ourselves as people that go into the field, hammer in hand, loaded with a compass so we can figure out exactly where we are out there. And then we go out to the field and we pick up solid rock. And it has to be in situ. That's a Latin term for something in place. So if the rock is not in place, it's worthless. So we go to the field, find some mountain or ledge, and pick up that rock that's in situ. And before you touch it, you have to measure the orientation, so you can mark an arrow on it, the north arrow, and then cut a piece, and then take that piece, go to the lab, make a thin section, look under a microscope, and tell us the history of the Earth. If you go to the desert, there are no rocks in place. What you find is rock rubble, a mixture of rubble and sand and so on. Those are really very little things for the conventional geologist to see. I came to understand this very clearly when in 1975, well, no, I'm sorry, before 1975, maybe 1973, when NASA decided to cooperate with the Soviet Union in the Apollo-Soyuz test project, and as was assigned to be the principal investigator for Earth observations and photography. And one of my jobs was to bring in the best talent in the country to teach the astronauts about all of the surface features of the Earth. So I did. I brought in the people that will talk about the very cold regions. I taught the people that talk about the structures of the Earth and the San Andreas Fault and the cracks in the ground and so on. And they had the people that talk about agricultural fields and soils and so on, and got the people that talk about deserts. And there was a very clear distinction between those who spoke to the astronauts about all of these other fields and those who spoke about arid land. Very little came out. And when the astronauts would ask questions, these people would say, well, we don't know that. And where would these dunes, why would they form these dunes rather than these? Well, we never really found out the reason for that. And so when I realized that our understanding of the desert is hampered by these basic reasons I talked about, I thought perhaps we should utilize satellite images to study the deserts of the Earth. And that is quite possible because of, again, three reasons. The deserts are there because of the lack or scarcity of rain. So they are almost cloud-free. So you can take pictures of them all the time. If you want to take a picture of Orlando, Florida, or the Cape right here, you really have to wait for a while to get some cloud-free environments. But when you are in the middle of the Sahara, you can look down any time and take a picture. It'll be cloud-free. The second reason is that satellite pictures or pictures from space cover a very large area, so you can actually study regional patterns rather than restrict yourself to one small place, one small region. And the third is that the deserts, because of the lack of rain, have absolutely almost no vegetation. And if you have no vegetation, then the exposed rocks and sand with their colors, the colors are meaningful. So if you really understand the colors or the reasons for the colors of the exposed rocks and sands, then you have almost a soil map, a chemical map of the terrain, if you understand why is this brown color this way or why the reddish color is this way. And you'll see some examples of that. But all of these things that we learned about how to interpret satellite images really came from the origins of working with the Apollo missions, or the working for the Apollo missions to the moon. When we, as geologists, when we were asked at the very beginning, maybe about 2 years before the missions, to select or help select the landing sites on the moon. All right, how to do that? We had certain criteria. The place has to be flat, it has to be rock-free or boulder-free, and it has to be scientifically interesting. The only thing we had were pictures taken by unmanned missions, like Ranger, Surveyor, and Lunar Orbiter. So you look at the place and you say, all right, how flat is flat? The flat terrain that we had to select could not be, the inclination could not be more than 12 degrees, because if it's 13 degrees, the spacecraft would topple over. So how do we figure this? Because we had no topographic maps. So we worked on a system of the brightness values. Like we say, if a surface was like this and the sun is like there, then this would be absolutely white. And if it's like this, then it's called complete shadow, so absolutely black. And in between, there are all kinds of ranges of gray. So we measure the range of gray from white to the black, so figure out the tilt of the terrain. All right, we did that. Second is the blockiness of the terrain, because you cannot land in a place where they had very large blocks, because if you do, one of the spacecraft legs would land on these blocks, and also the spacecraft, the LEM, would topple over. So it had to be free of blocks, okay? How are blocks produced on the moon? Well, we thought either by volcanic explosion or meteorite impact. So the farther away you go from the rims of craters, the clearer the terrain, the lack of blocks. Fine, and then scientific interest. Well, it depends then on the interpretation of the terrain. So we learned all of these methodologies during these years. And it really is through this basic study of the surface of the moon that we began to learn the tools of photogeologic interpretation. And what I would like to do this evening is to take you through a journey of these 26 years of fascination with satellite images, from what we have learned about the moon, and then give you an example of this Apollo-Soyuz mission, of what we could have done, what we had done using the photographs and observations made by the astronauts. Then we'll move and show you an example of how we found great rivers in the Sahara, buried under sands, and we found the evidence from shuttle missions. And we'll go through to give you some examples about the correlations we have made between the surface features of the Earth and those of Mars. Get also an example of the application of remote sensing to archaeology, or investigations of a chamber at the base of the Great Pyramid in Egypt. And then we'll end up with what we're doing right now at the Center for Remote Sensing at Boston University, which is to compare satellite images of Kuwait taken before the war and after the war, to see exactly what has changed in the terrain, in the environment, since the Gulf War. So if we start with the slides, please. First slide. And we want to the lights down as much as we can, so that the pictures would look okay. Thank you. Nope. Yes. This bullseye is one of the views of what is called Mare Orientale, or the eastern basin on the moon, and it is on the west limb of the moon, and it's called eastern because the astronomers, when they looked at the moon, the picture was reversed, and they just thought that the east side of the moon is what they looked at, and while it really was the west side. And so you see here, this bullseye is one very critical thing about the moon, where we see rings upon rings around this dark area in the middle. This particular picture showed us that the very large features on the moon, that actually basically make all of the features of the man in the moon, are produced by the impact of very large meteorites or meteors or comets hitting the surface of the moon. This one right here is about over 1,000 kilometers across. And so all of the features associated with this impact event including ejecta from this feature, are the creations or the things that create the very light-colored material on the moon. So all of this material is original crust of the moon itself, and it is the light-colored material. And the dark material, very much like all of the stuff that forms the features of the man in the moon, fill in the basins right here and the boundaries of these basins. And we believed at the very beginning that all of that must be the result of volcanic activities, meaning something that came from beneath the surface. So before we went to the moon, we realized that there are actually two kinds of rocks on the moon: light rocks or white rocks and black rocks. The white rocks are the original rocks, and the black rocks, right here in the center and out here, are the ones that came in later from volcanic activity. So we looked at the craters and the crater forms, and we see that there are distinct features about impact craters with a very sharp rim, a mountain in the center, and very rough ejecta on the outside, as opposed to what we believe are volcanic craters, where you have kind of a subdued rim and very smooth interior where the lava cooled, and smooth outside as compared to all of the rubble from the impact ejecta. So we could make this distinction between things that were made by the impact of meteorites and those that were created by internal energy from volcanic eruptions, including things that are very much like the things that we see in Hawaiian volcanoes called the lava tubes, where lava would have moved in a tube beneath the surface and moved downhill, and then the surface of the tube itself would collapse, and then you end up with something that very much looked like a river, because the fluid flow of lava right through it going downhill all the way. So this way then we were able to figure that when we look at the whole moon, as Galileo did some 367 years before we started, he looked at a microscope and he actually looked at the moon and he said there are two things on the moon: the terra, which he called the continents, and the maria, the oceans. He believed that the dark areas in here are oceans very much like the Earth, so he called these the mountains or the continents of the moon, very much like the continents of the Earth, and these are the maria, the seas of the moon. So with all our investigations, we found out that, yes, he was right. There are dark things and white things, and the dark things, the light things, he is correct. That's very much like the continental rocks or continental crust of the Earth. And the dark things are made not by water deposits, but by volcanic action. So now we have a better view of what the moon is made of, and particularly after all of the investigations of the surface of the moon, where we have now samples from Apollo 11, right here in Mare Onculitatis, Apollo 12 from right here, Apollo 14 from this site at Ramaro, Apollo 15, which landed right here at the Hadley Rill, Apollo 16 in the middle of the highlands right here, and Apollo 17 at Littrow at the edge of this Serenitatis Basin. So after 6 lunar landings on the surface of the moon, we established beyond doubt that the moon rocks and the Earth rocks are similar. They are not identical. The moon had never had a water on the surface. It may have had a temporary atmosphere, but because of its gravitational pull, the atmosphere could not have stayed around the moon for very long. It has never hosted life. The elements from which the moon rocks are made are exactly the same elements that make the Earth rocks, but in different proportions. So the moon could not have come from the Earth, but both of them would have come from the same mother, so to speak. Yeah, because there were ideas about the moon that may have been the daughter of the Earth, meaning born from where the Pacific Ocean might be, or the wife of the Earth, something that was roaming around in the cosmos and then was attracted to the Earth by gravitational pull. But we've figured out that the moon must have been a sister of the Earth, born from the same mother, so to speak. So in addition to that, we figured out all kinds of things about how the crust of the moon compares to that of the Earth, And we can see that this is the side of the moon that faces the Earth. And we see that the center of figure is not in the center of mass, because the continental rocks, the light-colored rocks, there are more of them on the far side, and the crust of the moon bulges towards the outside more than the crust on the near side of the moon. And we also figured out the division of the moon all the way to the core, and we now know that there must have been a partially molten core or partially molten zone within the moon, because we measured earthquakes, and one of them resulted from, or moonquakes I must say, and one of them resulted from the impact of a meteorite on the far side of the moon. And we received the surface waves, and we did not receive the body waves, which means that even though there's something that impacted the moon, we could not figure or receive the wave that went right through the moon, and that happens only if there is a partially molten core or a partially molten zone where that wave would be dissipated. So we know a great deal now about the moon and the relationship between the Earth and the moon, and we can make an assessment of the chemistry of the moon from the Apollo 15, 16, and 17 actually carried. This one here was Apollo 16, and this was 15, and this was 17. The three missions carried instruments that actually tested the composition, the aluminum and magnesium concentrations on lunar rocks, and from them we also confirmed that the light-colored material right here has higher concentrations of aluminum, which is the light-colored rocks, and the dark areas right here have higher concentrations of magnesium and iron, and that we expect from the dark rocks like basalt. So now we have a history of the whole moon, the near side and the far side. This one here is the side of the moon that we see all the time, and this is the side that is hidden from us. And you can see there are very large circles which represent the impact basins on the near side and the far side, but we can see that there is a lopsided distribution of the dark volcanic material, a great deal more on the near side, covering nearly 35% of the surface, and very little on the far side, covering only about 7%, meaning that there is because of the gravitational pull on the side of the moon that we see all the time, much of the volcanic activity really occurred on that side rather than on the far side. So there is a great deal of relationship now between the Earth and the moon, and as the moon has affected the Earth has affected the moon. So now we move out of this story and we go into the applications of what we did on the moon to the Earth. And one of the things that we realized from the outset is that the astronauts, to be able to do a good job as far as observations and photography, they have to be trained to do that. They have to be trained on what they are looking at. And this here is an example of that, because Jim McDivitt was traveling around the Earth, and he looked at this structure right there, and he said, oh my God, we see a huge field of lava flows. And the volcano must be out of the view over here, that this must be, there is a volcano must have been here, and this is how the lava came in and then was deposited in this huge mass and so on. And he was looking at the Nile and the Nile Delta. So we knew that there is got to be some education here around here about what you see about it, and we began to educate the astronauts by just looking together at pictures of the Earth taken at different times from different orbits at different angles and so on. And this is the view of a training session with the Apollo-Soyuz astronauts, because we had begun with the Skylab mission and went more there to the Apollo-Soyuz mission. And here is one example of how some of these pictures could be used. This is the Nile Delta again, taken by the Gemini 5 spacecraft. All of the dark material here is agriculture around of the Nile Delta, around the Nile, from the Nile silts. And this part right here is part of the Mediterranean Sea. And this area here is Alexandria, Egypt. And all of this is desert. And the desert is naturally, in this particular case, is completely vegetation-free. This, when we looked at this picture, I saw a banding or a zoning right here. There is an area right here that looked mottled and very specific nature to it. And then an area right here that is kind of yellowish and reddish in some cases, but rather smooth looking. And then another area here with a different color with these few lines. So I went to the geological map to see what the local geologists have mapped there, and they found absolutely no reason for this zoning. So we asked the Apollo-Soyuz astronauts to take a picture of the same area, and again we see this zoning, the Nile Delta, Alexandria, the Mediterranean, and again this zone right here, and the smooth zone, and another one here. And it turned out that when we went out in the field right here, we made a straight line right here, stopping every 5 kilometers right through this to find out what the story is. And it turned out that this here is a desert pavement region. This here is a sandy area where the sand is moving back and forth. And this here is a soil that is a mixture of sand and clay and limestone. And so therefore it will be very good fertile soil. And as a matter of fact, that explained a great deal to us from the aerial picture, because here was the Egyptian government had started a desert reclamation program right here for 20 years, and they didn't really go much at all because it was started in this zone of sand. So it wasn't really a very good place to start, because when we compared the when we compared these two pictures to each other, we found out that the difference in 10 years of the border of vegetation from the Nile Delta right here and the desert has increased very little adjacent to the sandy zone, and increased a great deal in this wedge of mottled terrain near Alexandria, which means that this soil here is much, much better. So actually, if that picture and its interpretation was available at the very beginning when the Egyptian government was starting this desert reclamation program, they should have never started program here. They would have started right there where the soil is much better. And actually, we looked at this later in 1992. So we compared what had actually happened to the area between 1976 and 1992, and you can see the incredible growth of agriculture in this mottled zone that is closer to the Mediterranean. Just one example to show you how these photographs can really be used as soil maps if we understand the reasons for their color and the nature that we see in there. Now we move over to look at another story which had to deal with the space shuttle, particularly the first mission of Columbia, and one of the missions that carried the radar. This is a map of Egypt. This is the Mediterranean and the Red Sea and the Nile River right here. And that strip, the red strip, is the strip of radar images that was taken by the shuttle imaging radar instrument designed by a colleague of mine by the name of Charles Alachi at JPL. And we've been working on this particular desert right here. And I wanted to ask him to get us some imagery of this area. And he said, what is it like? I said, it's absolutely flat and sand. And he said, well, that will be a waste of film. We ain't going to see a thing. So I said, but if there are little features that will show up in the radar, it will help us a great deal, because we really see very little in the Landsat image. He said, no, I don't think you'll see anything at all. So I said, how about just a few seconds? He said, all right, we'll look into it. And he gave us 20 seconds of film. And indeed, it was the most interesting 20 seconds of film he has used. What turned out to be is that we have here as an image of from Landsat of the border between Egypt and Sudan. And here we see one little hill on the right and another little hill on the left. And everything else here is covered by sand, and all of these colors are different sand fields. So just flat terrain, very little to interpret. The two red lines are the 50-kilometer width of the shuttle imaging radar view that was brought to us in November 1981. So here now we see the reason behind one little hill here and one little hill here, the same ones, and that is because there is actually a river that moved out this way, and now I can see it and I can draw it right here. And there's another river that came together here. That's the confluence of the two, and then it went right here, and now I can make it up going out that way. So this here is an island between two rivers. And the third one is here, the island between that river and this very large one going out this way. So here is an area, this is 50 kilometers, this is 150 kilometers, where we have three rivers. One of them is 8 kilometers across, One is 12 kilometers across, and one is 20 kilometers across. And 20 kilometers is the total width of the Nile Valley. Not the Nile River, the Nile Valley, the whole thing. Okay, here we have 3 rivers, very close to each other, with that much water to form these rivers. So we thought that perhaps we should go down there and see what the story is, and we did, and went down to dig around the edge of this particular thing in here, the river right here, and we reached the ledge of that river at 16 feet deep. And down there we found all kinds of evidence of human habitation. We found all kinds of evidence of fires built by humans, and ostrich eggshells, and all kinds of hand axes and things of that nature, so that there is quite a bit of history all the way, dating back all the way to 200,000 years ago. At the confluence of these 3 rivers right here, I suggested to the Egyptian government to start a test well, just to see whether there is groundwater there, because if you have that much water, some of it would have evaporated, some of it would have gone to the mouth of these rivers, wherever they may be, and much of that water would have seeped through the rock. And indeed, they tested, and lo and behold, there's a great deal of water. Another well, and another well, and another. And they dug until 12 wells now under investigation and monitoring. And the water from these 12 wells is capable of, for supporting agriculture in 200,000 acres for 200 years, just from one location right here. Meaning that the amount of water that is beneath the surface of these deserts is enormous. So right now there is a test farm in this locality. So already all of that has grown from the local water. Here's a tanker and so on, and they have 5,000 acres of land that they're testing all kinds of crops in this particular area already, and the government is now figuring out whether to give it to little individuals or to give it to a large company for agribusiness to produce cash crops, or what to do, but nonetheless it will be utilized in agriculture. Next example will be somewhat similar, and we go back to the story of the desert. As I was saying, this is a view of the largest desert belt in the world, taken by the Apollo 11 astronauts after the translunar injection, or meaning as soon after they finished their job around the moon and they began their journey towards the Earth. This is the view of the Earth they saw, and the Apollo astronauts usually said that the region of the Middle East and North Africa is the only part of the world they could look at from the vicinity of the moon and actually see all of the topographic features and figure out the geography. The reasons go back to what I was saying. First, the desert is clear of clouds. Every white thing that you see in this picture are clouds. The dark areas are the oceans, but also the vegetated land. Here is, you see in here all of North Africa, and there is the rest of Africa, and there is the Arabian Peninsula, and here is the Red Sea and the Mediterranean and so on. See Europe, even though it is not cloud covered right here, but you don't really see much at all because of the vegetation right here. And the colors are very much like the dark colors of the water. And here we can see the colors of the desert, and all of these colors are meaningful chemically. So one could figure out exactly the chemistry of this land if we know what the reason for that particular color is versus this and so on. Now when we compare these deserts to each other, the best comparison we can come up with is an aridity index, which measures the amount of solar radiation that is received on any part of that desert to the amount of rain that actually comes to that same surface area. In the middle of this huge belt of the deserts of North Africa and the Arabian Peninsula is this line right here that is around the yellow area there. And that line reads 200, which means that the received solar radiation is capable of evaporating 200 times the amount of rainfall. All of the numbers in here vary between 10 and 50. And these are incredibly dry deserts. Just to bring this home, the driest place in North America is right here in the US, is Death Valley of California, and the number for that is 7. So you can see how dry is dry with 200. Now when we look in that kind of terrain, we remember Mars, because that is almost the same kind of condition. Absolutely dry terrain. Used to host water before, as we saw these buried rivers, but no longer has water, and the wind is the king. The wind is the only agent of transportation and erosion. And so when we look at the surface features of Mars, we see wind-blown features. Everywhere we see deposits of light-colored material with a little bit of reddish color from oxides of iron, something like oxides of iron, and you see these little dark streaks in the lee of topographic impediments. We see almost identical kinds of things in the deserts of the North Africa. Here is a case in Egypt along the border between Sudan right here and Libya on this side. You have this spindle-shaped dark area behind a large mountain, or behind a tiny little rock right here, a dark rock, and that spindle shape behind it like that, from the fact that there was a lot of light-colored material, sand, coming from the north, depositing around it on the left and around it on the right, and leaving this whole zone behind in the lee sand-free. And we only understood this after we made this investigation on the ground, where we have the hill and the sand deposited on that side and on that side. And because of the existence of this topographic impediment, this area here has been shielded from the deposition of sand, so it really is a sand shadow, so to speak. That explained things that we saw on Mars, and we actually misinterpreted at the beginning. When we saw this feature was a crater with a dark thing coming out of it. So we said, aha, a volcano. Here is the crater with the volcanic thing and the stuff that came out of it. Whether it is a lava flow or whether it is an ash deposit, it's the same thing. But turned out not to be the case, because that was the explanation. There is a crater, meaning a rise. All of the white material in here is wind-blown sand, came out this way, hit the edge of the crater right here, veered to the right and veered to the left this whole area behind the crater free of sand. That's why it is dark. So that is the original surface of Mars, and that is the deposit of wind-blown material, very much like this here. So we actually figured out what this Martian feature is after we studied the Earth landform. Also, another feature on Mars that we saw was the little blocks like that on the surface with streaks like this. And this we explained after we visited this place in Sudan, where we have little blocks and streaks like that, again from the deposition of light-colored material streaming through right here, and the lack of deposition from topographic impediments. In another way, we also could look at the pitted rocks on the surface of Mars and Earth and figure them out too. When we first looked at the right one right here on Mars, this looked very much to us like vesicular basalt. We have a rock called basalt that is brought in by volcanic action, and this molten material comes from beneath the surface of the Earth. The molten material has a lot of gases with it, and if the material is cooled very fast, is chilled fast, then the gases don't have time to escape, so they make little pockets. So they can make vesicles very much like pumice. And so we call it vesicular basalt. And so we thought that this was vesicular basalt, and that's the case, and ended the discussion until we saw in the western desert of Egypt, in this very arid terrain where there is no water and so on, and the wind actually works on the surfaces of any rock. It could be igneous, it could be sedimentary, it could be any type of rock, and actually the wind makes these surface pits. So all of these pits could be wind produced, and it turned out that the likelihood is that for these things to be also little pits that are produced by wind erosion of the surface of exposed rocks, so it did not have to be vesicular basalt. So these comparisons were certainly very important to our understanding. And now I'll move into one of these very interesting things, and how do you apply remote sensing to archaeology. At the Center for Remote Sensing at Boston University, we have under that umbrella the departments of archaeology, geology, and geography. And so we have been trying to entice the archaeologists to utilize these tools, the pictures and the instruments and so on. And one of the cases that we have established beyond doubt the use of remote sensing instrumentation to the study of archaeological sites is at the base of the Great Pyramid. It's an air view of the pyramids of Giza. This is the largest, the Great Pyramid. In 1954, a chamber was opened at the base of the Great Pyramid right here, and that was also a very interesting story how that started. And it started by a visit to Egypt by the Emir Saud, the son of King Abdulaziz of Saudi Arabia. And he went to visit Egypt, and the King Farouk took him in his red car, sports car, to show him the pyramid. And he went around, and he could go, at that time, you could go around the pyramid on 3 sides, but you could not go on the south side, because there was a huge pile of rubble covering this whole area right here. And the Emir of Saudi Arabia asked King Farouk, why can't you get this rubble removed? Don't you have money, or what is the story? The king took it and cringed, and then called the head of the Service Antiquité on the following day, and they said, I want this rubble removed tomorrow. So it took them about 2 years to remove this rock rubble in case there are cultural things in it. And as they completely cleaned it, they found all kinds of fascinating things that they never knew existed. Amongst them are 2 series of blocks, each one covering 100 feet. And each block is about 15 feet by 3 feet. So huge blocks of limestone in the rock at the base, right at the base of the Great Pyramid. So they opened one of these blocks. They begin to smell the smell of cedar wood. And as they opened more and so on, they found a disassembled boat. And they took out the boat and assembled in that fashion. And they actually put it in a museum that is right there. That's the museum right here, which was built right on top of the site of discovery. So when you go to Egypt next, you should see this thing. It is fascinating. It is the oldest post in the world, 4,600 years old. Magnificent structure, and supposed to have had something to do with the funeral of the Pharaoh Khufu, or Cheops, the builder of the Great Pyramid. Now they found out that the ancient Egyptians had put the pieces of wood, the disassembled pieces of wood together, and actually tied them together like that. And in many cases they would have markings on that wood, a scribe looking this way and one looking this way, and meaning so that you can actually get these 2 pieces facing each other and so on. Like when you go and buy something from Sears and you say, take point A and make it look at this point B and connect them together. The ancient Egyptians had also left kind of instructions to how to assemble the boat this way. And the way they had actually stored it beneath the ground was ingenious. That is the mound of debris that had been on the south side, where in the past, one could not pass through the south side. And this was the pit that was actually buried, or the chamber that was buried by this debris. And the chamber itself is a pit about 100 feet long and about 15 feet deep. And this one here was about 15, the blocks on top about 15 feet long. And then the ancient Egyptians mixed sand and limestone and lime, and they actually made a mortar that nearly sealed it, nearly hermetically, because the people that opened the pit at the first time, or the first block, did smell the cedar wood. So we thought that there may have been an honest-to-God hermetic seal on top of that, so we decided that we would look into this with the remote sensing equipment and the techniques to see whether we can actually go inside, photograph what is inside, sample the air inside in case it is still hermetically sealed, so we would have a sample of the atmosphere of the Earth that is 4,600 years old, measure the temperature and pressure and all of the environmental conditions, and seal the whole thing as if nothing happened. And we did that. Started with the ground penetrating radar to see the instruments, and then we joined with people from NOAA at Boulder, Colorado, to prepare for the sampling of the air after an airlock had been designed to make absolutely certain that when we drill a hole to go through, there is no mixing between the air inside and outside. And then take a camera and look inside and see what the contents are like. From the first pictures that we took, we knew that we're not really dealing with a sealed chamber anymore, because of all of the white pieces. All of this is the wood, the disassembled boat right here, and all of the white pieces are pieces that had fallen off the roof from the cement between the blocks. And we realized later that at the time of building of the boat museum to house the first boat, there is not very much space between the boat museum and the Great Pyramid. So the cement mixing machine and the brick making machine and so on was put on top of this second boat, shaking the rocks and spilling water and so on. So there had been a seal, a breaking of the seal. So when we finally got the age of the air that was taken, it turned out to be 2,000 years old. So it is no longer 4,600 years, or no longer air of today. So there has been a mixing between the ancient air and present day air. However, it was the hole that we drilled was absolutely sealed. So we established now that we have the technology to go into some place and completely investigate it totally non-destructively, so that we can preserve the site itself, because the site in itself may have archaeological significance. So now we say as an example, and many people, many places in the world now have begun to contact us about trying to investigate something like that. In Guatemala, that's a pyramid that's closed, and a tomb in China and things of that nature. So we established the use of the technology in archaeological investigations. The last topic is the topic of today, what we're doing right now to compare satellite images of pre- and post-war in the Gulf to see what had actually happened to the surface of Kuwait. And this is a view from NOAA satellites of the Gulf region. And the Gulf is called the Persian Gulf by Iran and by most people in the West, and it's called Arabian Gulf by everybody in Saudi Arabia and Kuwait and Egypt and places like that. So I'll have to be very careful where I'm giving lectures to name this Gulf the Arabian or the Persian. So right now I'll just call it Gulf. So so now this is, all of that is Iran, and Iraq is right here, and Kuwait is just a little tip right here in the northwest side of the Gulf. All of this is part of Saudi Arabia, and this is the island of Bahrain, and this is the peninsula of Qatar and the United Arab Emirates and Oman. So there are a whole bunch of countries that are connected. All of it is desert. All of it has these numbers that vary between 10 and 50 as far as aridity is concerned. And as soon as the liberation of Kuwait began, you remember the well fires in Kuwait right here. I'll show you the Landsat image of this area right after that, where you see in this image each and every white dot right here is a well, an oil well on fire. And all of these horizontal lines are actually the sensors on the Landsat satellite turning themselves off, because they're measuring temperature so high that they think that there is nothing on Earth like this. So they think there's something wrong, so the sensor actually shuts itself off for a while to correct and go back to measuring. And it's because of this incredible energy that was emitted from the well fires. All of this, the well fires created incredible the storms or plumes, and these plumes covered a great deal of the land in Kuwait. This is a photograph that was kindly sent to me by my friend Jane Hodges, and where one can see that the direction of the plume, which is a little bit different from the regular direction from the north towards the southeast. And some of the shuttle images are very useful, as a matter of fact, because they were taken at times when we could not get images from Landsat or Spot. And that also shows the utility of when you have astronauts in a spacecraft, and when you have the spacecraft at different altitudes at different times. So many of these things can be very useful. They add to each other. And when we looked at all of the data taken by Landsat and Spot and the shuttle and so on, we figured out that there is a whole region of the Earth that was affected by the plume that came from the well fires, which is the blue line right here. And that area represents material that came in from the dust in the air due to all of the military activities and turning up a great deal of dust from the well fires. and from covering so much of that water by the oil spill. All of the material that was launched into the atmosphere with the wind, which is the plume from the well fires and from the dust, actually affected the line of the monsoon clouds of India, or the Asian subcontinent right here. And what we have is a pressure zone that shifted that line southward, causing a lot more rain in the Indian Ocean and in southern India, causing very little rain for 2 years in Pakistan and northwest India, and causing also very little rain in Somalia and Ethiopia, causing droughts there, and no rains right here. So actually there was a great deal of regional meteorological effects that resulted from the Gulf War, and only God knows really what else happens, because when you move this high pressure zone that we used to be right here southward, then the cold pressure, the cold weather from the Mediterranean moved inland in here, and there was all kinds of snow in Jordan and Israel and even in Kuwait during the last 2 winters. So when that system moves down here, only God knows what else moves and so on, because it's all connected. So the regional effects may have had also some global effects that we really don't know about. This is an example of how much oil was on the water in the Gulf. And that oil affected the desalination plants, and much of the oil was sucked out of the ocean and actually dumped into huge pools like that. And to these days, nobody really knows what to do with these pools now. That's oil that was pumped out of the Gulf water and now stored in pools in the deserts after they cover the desert region or the pool area with plastic, so that the oil would not seep to the groundwater and so on, and they remain right here. Pool after pool after pool, with huge areas covered by oil that no one knows what to do with. The last item that I wanted to mention was the effect on the desert surface itself. The desert is a very fragile environment. It is stabilized completely when it is absolutely flat, because the wind really would like to move over a very flat surface where there are no obstacles. So as soon as, and that's why the desert is flat in many ways. So the wind creates a flat surface, and that flat surface is protected by a layer of pebbles, the size of a pea to that of a walnut, that actually armors the fine-grained soil beneath it from the action of wind. So the wind comes in, bounces on top of these grains or pebbles or cobbles, and leaves the soil alone. Now, when you remove that layer of pebbles, as in digging trenches and pits and hiding places for tanks and ammunition and so on, then you're actually disturbing the desert surface considerably by creating new sources for the wind to carry sand, and this sand accumulates and forms sand dunes. So right now there are all kinds of sand dunes blocking roads in Kuwait. That started from the war itself. So right now we're actually looking at all of the regions that may have been affected by the disturbance to the desert surface from these military activities on the desert of Kuwait, specifically so that we can figure out areas that need attention as far as remediation of the problem is concerned. And we're doing that by comparing satellite images taken before, during, and after the war, and making a map of the change and figuring out what that change is specifically. So with that, it is just another example of the kinds of things that we can apply space photography to in understanding the environment of the Earth, as well as those of the Moon and the planets. And one of the things that I wanted to say was the fact that we in the sciences out there doing our work quietly, we also know that one of the most significant aspects of the whole thing is the ability to have these pictures available to us, and we know that we could not have that without having a bunch of dedicated engineers and scientists working within the NASA centers to make absolutely certain that these programs are achieve their objectives, and you can be certain that each and every item that we get out of your productive work, we will put it to great use, not only to understand the Earth for the basic science, but also to help people worldwide. Thank you very much.
Does anyone have any questions for Farouk? Okay. On behalf of NKMA, I'd like to say thank you very much for a very, very fascinating.
Wonderful. My own shuttle. I can come back easy now.
And there's also a book about the shuttle autographed by some of your old-time colleagues and friends here at the Center.
Right. Thank you very much.
I think we all enjoyed that tremendously, and as Farouk says, the scientists working very quietly, I think we forget some of the tremendous spin-offs of the space technology and how it can be used to benefit mankind, and hopefully we'll continue having scientists like you working with us to make that happen.
Thank you.
Thank you.
Thank you very much.
And now we'd like to end with a benediction by Michael and his team of singers. And then if you did want to join in with us as we exit with our Desert Storm theme song, many of you know I was in Germany throughout the war, and we probably heard this song at least once a day. So if you'd like to join in with Lee Greenwood at the end, we'd appreciate it. Thank you.
God be with you till we meet again, with his sheep securely fold you. God be with you till we meet again. Does everyone have the words?
If tomorrow all the things were gone, I'd work for...
On the outskirts of the city of Cairo stands one of the most famous and mysterious monuments in the world, the Great Pyramid at Giza. It was built by the pharaoh Khufu, sometimes called Cheops, around 2600 BC. In the centuries which followed, these weathered stones, 2.5 million of them, have revealed their secrets slowly, piece by piece. No one really knows why the ancient Egyptians erected these massive structures, but tantalizing clues keep turning up. And sometimes they take the form of buried treasure. In 1954, an underground vault was discovered beneath these capstones near the pyramid's southern base. Inside the vault, explorers found the remains of a boat, a very big boat.
But I remember seeing some.
Farouk El-Baz remembers the stir the find caused.
The news of the day said that we had found a ship that's kind of the funerary boat. When they removed the pharaoh westward, sailing westward with the sun, so that he'd be buried in this place. And a lot of people expected, now they're going to find his body, the mummy, because the Khufu's mummy had never been found.
Tuhami Mahmoud Ali was foreman of the work crew in charge of the excavation.
أول حجر
وكان شعورك ايه ساعتها؟
كنت فرحان عشان وجدنا مركب مش في العالم.
I was delighted because we had found a ship, and the likes of which didn't exist anywhere in the world.
Tuhami was among the first men to enter the vault in nearly 50 centuries. But instead of the pharaoh's mummy, they found a completely disassembled ship, 1,224 pieces of polished cedar, arranged, in the words of one observer, like parts of a toy model. It took 15 years of painstaking labor to put the boat back together. The old shipbuilding techniques, like hand-tying planks to the rails, were scrupulously followed. Naval historians say the boat is an engineering feat in wood, as impressive in its own way as the pyramids are in stone. But even as the vessel took shape, experts disagreed about how it had originally been used. Some said it was simply a funeral barge. Others believed it was a ship for the pharaoh in his afterlife. Hieroglyphs from the nearby pyramid of Unas suggest that a pharaoh was expected to sail 2 boats, one during the day and one at night, as he followed the sun throughout eternity. Other reliefs, like these on the walls of the tomb of Ti, provide documentary evidence of the importance of boat traffic on the River Nile, but shed little further light on the debate, except to show us how the ancient boats were made. But whatever its use, the 142-foot vessel must have made quite an impression then, as it does today. It is the oldest ship in the world. Housed in its own museum, Khufu's boat attracts some 200,000 visitors a year.
For the anchor, and the big one, you got to push it away from the bank. But this is small cabin for the captain, and this the big cabin for the mummy of Cheops. This is all cedar wood.
34 years later, scientists are preparing to examine the contents of a second underground chamber, discovered a stone's throw away from the first. But this time, there are no plans to excavate it.
Because I bet if we measure from the...
Dr. El-Baz, director of Boston University's Center for Remote Sensing, and a team of scientists sponsored by the National Geographic Society begin the operation with ground-penetrating radar, which has provided a rough map of shapes below the surface. This space-age approach is helping to solve one of archaeology's thorniest problems: how to explore a site without destroying it. The only digging involved will be scraping away a few feet of loose earth from one of the enormous capstones covering the pit.
Archaeology is no longer a grave robbing activity or a destruction, a way of destroying things until you get the artifacts. It's no, because the site itself might be an artifact, to keep it intact the way the ancients had left it. So this is really getting a way of departing from the archaeology the way it was, and we are just opening a whole new way that might apply in many other fields.
The key to the plan is drilling a small hole through the 6-foot-thick capstone into the vault, but it must be an airtight hole. When the first chamber was opened in 1954, the air inside was still heavy with the smell of cedar. So there is a chance the air in this vault has been trapped there for over 46 centuries, an invaluable scientific find. Bob Moores of Black & Decker developed a sophisticated airlock that will make sure new and old air don't mingle. Anchored to the rock is a system of O-rings and backup seals. The drill will move through the limestone at the rate of about 4 inches an hour, with frequent pauses to remove dust and debris. Moore's unique design then allows the hole to be closed, while other instruments are inserted. The key to the plan is drilling a small hole through the 6-foot-thick capstone into the vault, but it must be an airtight hole. When the first chamber was opened in 1954, the air inside was still heavy with the smell of cedar. So there is a chance the air in this vault has been trapped there for over 46 centuries, an invaluable scientific find. Bob Moores of Black & Decker developed a sophisticated airlock that will make sure new and old air don't mingle. Anchored to the rock is a system of O-rings and backup seals. The drill will move through the limestone at the rate of about 4 inches an hour, with frequent pauses to remove dust and debris. Moore's unique design then allows the hole to be closed, while other instruments are inserted. Inside the vault, air samples will be collected and tested for traces of modern air pollutants. If none are found, it might explain why the first ship was so well preserved. Peter Tons of the National Oceanic and Atmospheric Administration will supervise the sampling procedures.
The boat in the adjacent pit to this one was extremely well preserved for 4,600 years. And from what I've heard, it has deteriorated more in the past 20 years than in the previous 4,600. So the Egyptians are not very keen on opening this pit and getting the boat out, or if there's a boat in there, of course, and then have it crumble. So they would like to see what's in there, what it's like in there, and then seal the hole back up.
The drilling operation consumes one full day and another. Then, midway through the third day, Bob Moore's drill moves through the last few millimeters of stone.
Break through. Break through. Hey. All right.
Wait, I'll pump on this for a little bit. Because I want to film.
Now it is time for the rest of the team to go to work. Peter Tons will draw about 70 liters of air from the vault.
Are you going to take any samples for the... Yeah.
Since the results of the analysis won't be available for months, Tons decides to perform a less scientific examination on the spot.
They smell stale.
Thanks.
It smells stale, guys. No, definitely does not smell like cedar. Absolutely not.
It is nearly midnight before the photographers get their turn. The long black tube is part of the special video system designed by Pete Patrone of National Geographic.
What does monitor look like, anybody?
In order not to affect the temperature inside the vault, a heatless lamp will provide the light.
Turn to the left slowly. Good. It's the first time we've had in a vertical position to work on it.
As the camera begins its slow descent through the hole, everyone gathers around a TV monitor to catch a first glimpse of things that haven't been seen for nearly 5,000 years. An eerie shower of drilling dust signals the camera's entrance into the space which has waited so long in darkness.
Neat. Good job. Right. Oh, some good men do it. What do we do?
Oh, nice. God, bless Gertie.
Hey, okay, you're right. It is a boat.
Yeah.
That's not dirty laundry.
Look at all that stuff on top. Well, it comes from the ceiling, I think.
Ooh.
Pieces of limestone, I guess.
Right.
Don't you think?
It does look like pieces that flaked off the, maybe the sealer. Gypsum sealer.
Oh, yeah, that's it.
Beautiful. Beautiful.
Pieces.
It's like a man.
That is gorgeous. Gorgeous.
Tuhami has no doubt that he is looking at the pieces of a second ship. The camera shows a notched beam that supported the deck house roof, a valuable clue to the length of the ship. Other angles reveal a copper fitting, a stonemason's ancient calculations. Experts believe each piece is part of a ship very much like the first, though perhaps a bit smaller. The obvious damage inside the vault may be due to a brick-making machine used to build the museum for the first ship. It stood directly above this second chamber, vibrating and dripping water. Other details seem to confirm this hypothesis. Wet-looking patches in the roof where plaster has fallen. A pair of ghostly oar blades, warped by moisture.
No, drop down.
And then, something unexpected.
Peter! Quick! Come on, Peter! 4,000-year-old there. Yeah. Go, Peter! Go! Great! Look at that little dude go. 5,000 years ago. Righty, man. This is daughter of Cheops.
How else could the beetle live? You know, I mean, he has to be breathing air. So if we have a live beetle, that means we don't have 4,000-year-old air. Whatever the results are, bad or good, if they're scientific, that's what we tried to do. We tried to find out. And we did find out there's something living down there.
After taking samples of the air and after looking at it, we know that we have not disturbed the site at all. So this is kind of starting a whole new, opening a whole new door to technology, and I personally believe that this might be a new change to the archaeological exploration, very much like what age dating did to archaeology earlier in this century.
Age dating propelled archaeology from a collector's pastime into a more exact science. Video exploration promises to extend its reach into realms that have always seemed impenetrable. Until now. And for now, at least, there are no plans to restore the Pharaoh's second ship. Soon the camera will be withdrawn, the hole in the stone resealed. Instead of seeing the vessel in all her original glory, visitors will have to imagine what it might have looked like, bearing the Pharaoh down the Nile, or even perhaps through the afterlife, in his relentless pursuit of the sun.